Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. We're doing problem number 4.13 from Elementary Principles of Chemical Processes, 3rd edition. The problem says, a pharmaceutical product, P, is made in a batch reactor. The reactor effluent goes through a purification process to yield a final product stream and a waste stream. The initial charge, feed, to the reactor and the final product are each weighed, and the reactor effluent, final product, and waste stream are each analyzed for P. The analyzer calibration is a series of meter readings, R, responding to known mass fractions of P, xP. That's the mass fraction. Okay. So then they give us this information here, this thing right here, the calibration data. And then it says in part A, it says plot the analyzer calibration data on logarithmic axis and determine an expression for xp, which I say is WP. xp equals WP in my thing. I always write mass fractions as with a W, a little w, and mole fractions with an X, just a habit from keeping track of these things when you have multiple phases and reactions and things going on. The standard that I used in my practice was W is a mass fraction, X is a mole fraction in the liquid phases, and then sometimes if you have like a gas phase, you use Y, or along those lines. Anyway, it doesn't matter what letter you use. I'm just using what I'm used to. They have XP in their thing, so yeah, there you go. All right, so logarithmic scale, like they were saying, logarithmic axis means that you are using this equation. If you don't remember how to do this, this is a little bit of stuff from, I believe, chapter 2, where you do some of this kind of stuff. If you need help on this kind of thing, I think you can go back to it's either chapter 2 or chapter 3. I've done all of the problems from those chapters, so just go ahead and go back and look into that and how to get more details on this. But basically, a logarithmic scale is this, which is a line. This is y. This is x, or sorry, this is your intercept. This is your slope, and then this is x. So I symbolize those with those symbols. Okay. So A and B are just adjustable parameters. That refers to this A and this B. Sorry, I'm using B here and B here. I'll represent the intercept B as always having a line, a bar above and a bar beneath. And this B is just an adjustable parameter in this equation, which also corresponds to the slope. Okay. So basically you do a best fit line, saying this is your y, x, and your slope, and your intercept. Okay, so the best linear fit is this, which corresponds to a certain A and B. So B equals this, and A can be derived from the intercept there. Okay. Oh, I did write them down. Okay, so B is this and A is this. Anyway, then you could use these parameters that adjust for the best fit in this equation. Okay. And then you can rearrange this equation to also solve for, okay, given an A and a B and you're given an R, you can calculate what the mass fraction should be. Okay. That's a lot of arrows. Sorry about that. Hopefully that makes sense. I'm explaining that well enough. If you have more questions, just drop a question in the comment, and I'll get to that. Okay, so for part B, it says the data sheet for one run is shown below. Okay, so then they give us a bunch of data. This is our given data here. Okay, they give us the mass of the initial charge. They give us the mass of the product stream there, number 4. And then they give us not directly information about the mass fractions of these streams of P, but they do give us R, and R, we know, can give us WP. That was the whole point of that first part that we did. So they give us an R, so we can calculate what WP is. Okay, so there you go. Those are the R's, and those are the corresponding WP's, just using that equation. Okay. Then it says to calculate what the mass fraction or the yield is. So it says calculate the mass fractions of P in all 3 streams, then calculate the percentage yield of the purification process. That's what this YP is. That is the percentage yield. Okay, and this is the equation they give us for the percentage yield. So if we need to figure out how many kilograms of P are in the final product, well, we have the total mass of the final product, and then we have the mass fraction of P in the final product. Pretty self-explanatory, right? This is the total mass of the reactor effluent stream, and then this is the mass fraction of P in the reactor effluent stream, times 100%, which changes units from a fraction to a percent. This is the total percentage yield, 96%. What they don't show is that this has a pretty big plus or minus some error. You know, we don't know how big that error is. Every measurement has an error, and especially after you do a bunch of calculations, like, you know, doing all this stuff up here and this, and then once you get to your final product, you know, plus or minus a certain amount of error, like error propagates all the way through. I'll talk a little bit about that later, but just keep that in mind, how we've done all of these processes in order to get our percentage yield. Okay. Right here, I just wrote down what those values were just to make this calculation a little bit easier, right? Okay. Part C. You are the engineer in charge of the process. You review the given run sheet and the calculations of Part B, perform additional balance calculations, and realize that all of the recorded run data cannot possibly be correct. State how you know. Itemize possible causes of the problem. State which cause is most likely, and suggest a step to correct it. Okay? Well, here's my analysis of how I know that not all of the data can be correct as written, right? Okay, so we know, I just do a mass balance here. We know the mass of stream 2, and we know the mass of stream 4, so we can calculate what the mass of stream 3 is, right? There you go. Well, we also know what the mass fraction of P is in stream 3. So let's do our mass balance around P. This is our mass balance around P. And the mass of P in stream 2 should equal the mass of P in stream 3 plus the mass of P in stream 4. Well, when you add those things up, you find out, uh-oh, this is my uh-oh face, you know, they do not add up. Uh-oh, that's not good, right? They don't add up. Why are we teaching you these things if it doesn't work, right? Panic starts to set in. All right. Well, what is the most likely cause of something like this happening? Well, like I said before, when you measure things, your measurements are going to be, you know, off by a certain amount. Like, you can never get a perfect measurement. There's always a certain amount of error associated with any measurement you make. And especially the demon of extrapolation was used in this process. Now go back and remember, look at this data that we collected. Data goes from R's that are associated with 100 to about 350, 360, all right, right? So we use data in this range in order to calibrate our perfect little function here, right? Well, take a look at the r's that we used in order to calculate the actual weight fractions that were in our stream. Oh, those are actually way outside of range. So we extrapolated. That's the definition of extrapolation. When you extrapolate, you are prone to very large errors. Okay, so that is a good example of why extrapolation is bad. If you are planning on using, R values in this range, then your calibration should not be in this range. It doesn't even make sense. Like, why would you use a calibration that's like way lower than the range that you're actually intending on using, right? Okay, so as the mechanics say, there's your problem, right? Okay, so that's the most likely cause of this, that there's just an error in your calibration and you work through it. If you recalibrate and you find that this is still the case, well then yeah, you dig a little bit deeper and you say like, hey, are we losing, let's take a look at our process here. Our process here is like, okay, maybe we're not getting everything out of the batch that we thought we were. Maybe there's some waste coming off here, or maybe there's like a leak in the reactor and there's like a fifth stream here that we don't know about because we're like losing stuff. Maybe the flow meter on this is not measuring correctly, or the flow meters here and here are not good. Yeah, so you just start digging and looking into all the different possible ways that this could happen based off of the different measurements you have. So, and then you have to physically go and look at the purification process, and maybe you'll find out something weird's happening. Like, hey, there's a bunch of mice got into our thing and shoot a hole in this product, or yeah, whatever. Well, that is it for problem number 4.13. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you'd like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.